Shabab, last time we talked about the first law analysis for combustion system, so first law of combustion system, and we said actually that we have two kind of system. We have the open system and the closed system, and we have considered the application of the first law of thermodynamics for open system, a steady flow. When we have an open system under a steady flow condition, and we are talking here about the combustion system. So open system, steady flow, so most probably we are talking about internal combustion engine and also the open cycle gas turbine, in which we have the system is open, we have flow in and the flow out, and also in addition to the combustion, then we can apply the first law of thermodynamics in this case. And we said if we have any systems like internal combustion engine, or if we have gas turbine, in both cases we have fuel plus air are provided to the engine, then they burn actually in exothermic reaction, then they generate part of the heat inside, they generate heat inside the engine. This heat can be converted to work, either to drive the piston to generate actually inline motion or reciprocating motion that can be converted through the crankshaft to a rotary motion. This is the case of internal combustion engine. In case of gas turbine, in this case, we can have the exhaust gases to run the blades of the turbine. This process may be associated with some heat lost or added to the system, because we can generalize the case for any combustion system. In some cases, we may have an endothermic reaction. The reaction actually may need heat actually to proceed for any other open system other than internal combustion engine or gas turbine. So this heat exchange direction can be added or rejected. This work, we can generalize the case other than the internal combustion engine or gas turbine. We can say the work can be added on the system or rejected from this system or produced by the system. And at the end, we should have actually the combustion product or the exhaust gases. And based on that, we have applied the first law of thermodynamics. We have proved actually that that should equal to the difference Q minus work should equal to the difference between the enthalpy of the product minus the enthalpy of the reactant. And the enthalpy, are you following me, Shabab?
Yes.
طيب, the enthalpy of the product or the reactant, when I need to calculate it, this bar ya shabab means this is calculated in kilojoule per kilomole fuel. So all of the calculation are done actually per kilomole fuel, as we write down the combustion equation for 1 kilomole of the fuel. So that should equal to the summation of number of moles, either for the product or the reactant, multiplied by the enthalpy of formation plus delta H. And this is the enthalpy, how we can calculate the enthalpy. This enthalpy of formation plus delta H are calculated from table A3, which contains actually many subtables in which at a given temperature we can get the value of delta H. And for a given species, like let's say carbon dioxide, you will find here actually the value of enthalpy of formation will be given in table A3 as well. But for the fuel, if I need to calculate the enthalpy of formation for fuels, like let's say methane, propane, butane, any fuel, you will find actually the value of enthalpy of formation is listed in table A4. So in table A4, you will find the list of fuel, and you can find there the value of the enthalpy of formation of any fuel in this case. If we need we have a combustion product or reactant or part of the fuel, we have a species that is not listed actually in table A3. So if the species is not listed in table A3 and I want to calculate the value of delta H, we have delta H is equal to CB dt. So if I need, this is delta H, is a differential form. If I need to calculate this difference, I have to do the integration. There are two approaches, one approach we call it the constant specific heat analysis. We can take this specific heat as constant, take it outside, so delta H will equal to CB average multiplied by delta T. And this delta H is the enthalpy at any temperature T minus the enthalpy at temperature equal to 25 degrees C. So the reference temperature is 25. So this delta H will equal to CB average multiplied by the temperature that we need to calculate delta H at this temperature minus 25. But this temperature يا شباب should be in degrees Celsius, as this one is in degrees Celsius. If this one is in Kelvin, it will be 298. So in this case, this temperature should be in Kelvin. But usually يا شباب, we need this delta H. We need it actually per kilomole. So that means this specific heat should be per kilomole in this case. And we said the specific heat per kilomole should equal to specific heat per kilogram multiplied by the molecular weight for this species. And the specific heat and the molecular weight per kilogram, the average value and the molecular weight, we can get them from table A1. Okay, is that clear, Shabab? So if the species is not listed in table A3 and I need to calculate delta H, so delta H will equal to CV kilojoule per kilomole Kelvin multiplied by the difference in temperature delta T. And CV per kilomole is equal to CV per kilogram multiplied by the molecular weight. The molecular weight for any species and the specific heat are listed in table A1. So this Shabab approach, we call it the constant specific heat analysis, in which we take the specific heat as constant and we say delta H, you can take it outside, it will be integration of delta T will equal to delta T. But in some cases Shabab, or the usual practice actually, this delta T, this CB is function of temperature. So usually for most of the gases, if you look at the distribution of the specific heat as function of temperature, it is almost a third order reaction. Okay, so in this case, if CB is given as function of temperature, so just take this CB, do the integration, and calculate delta T. This integration will be from temperature 298, which is 25, to any temperature T. Okay, sorry, so the table is just. So here it is, Shabab. So this is table A1. You will look in table in this table A1. You will find here the value of a specific heat is given. CB at constant temperature, CB at constant volume, and the specific heat ratio are given. Also, the molecular weight of the substance is given in this table for a list of substances here. Okay. If you look at table A2, you will find here, Shabab, this is the exact analysis. If I need to calculate, if I have CB in this case as function of temperature, as you can see, CB is function of theta, and theta is the temperature in Kelvin divided by 1000. So theta is representing the temperature in a way. So this is the equation. For a list of substances here, you will find actually the formula is given like steam, air. You will find the value of the constant. CB is equal to constant C naught plus C1 multiplied by theta plus C2 by theta square. C naught, C1, C2, C3, all of these constants are given for a given substance. So in this case, if I ask you an exam or something, and I will not ask because the function you find the function actually is in the exam is not just to check for how to use the calculator, but this is the situation. If I give it to you for any reason, maybe in the homework, if I give you CB as function of temperature, then you can do the integration, and from table A2 I can get those constant of the specific heat for the given species, do the integration, then we can calculate delta H. But most probably, Shabab, we will be giving the value of delta H we can get from table A3. Is that clear, Shabab? Is it clear? This is Shabab. This is what what I have done last time for a steady flow open system, how to apply the first law of thermodynamics. Like what if we have closed the system? Like in this case, we don't have mass transfer. Just the product, the reactant, fuel plus air are inside a tank, closed tank or rigid vessel or container, and in this case we have initiated the combustion. So it will be a kind Shabab in case if we have explosion or something in a closed medium. So in this case, how we can calculate the heat transfer in this case. So the second case, if we have actually a closed system in this case. So if we have a closed system, like say we have a container, and this container containing actually fuel plus air. For any reason, we have initiated actually the combustion, and in this case, this fuel plus air has been converted to the combustion product, and some heat has been released actually out of this reaction in this case. Right. This is a container, so we don't have mass in or mass out. The fuel plus air are just inside. So this is representing the case, Shabab, if we have closed tank, or rigid tank. When I tell you I have a rigid tank is that means it does not allow for mass transfer. Or when I say I have a rigid vessel. Or also the case of closed system combustion is representing actually the constant volume combustion in gasoline engine. If you remember the gasoline engine, this is the engine, and the charge actually inside the cylinder is fuel plus air. Once actually at the end of the compression stroke, once the spark plug initiates the combustion, then in this case the combustion should occur inside the cylinder instantaneously at constant volume. If you look at the representation of this cycle on the pressure volume diagram, if you remember, this is the compression stroke, and at the end of the compression stroke, the combustion takes place at constant volume. Then we have the expansion stroke. So this is constant volume combustion is a kind of instantaneous combustion in which actually the combustion takes place while this piston is not moving, just instantaneously. So we can consider this. In this case, we did not apply mass transfer. Just as the spark has initiated the spark, fuel plus air are inside the engine. So in this case, we have instantaneous combustion in gasoline engine. So that means this is the case when we have constant volume combustion in gasoline engine. So in case of gasoline engine, we have instantaneous combustion at constant volume, in which we can consider the system as a closed system. And this is an example. Type part of the heat generated here, Shabab, maybe we have some of this heat is rejected, or in some cases, as I told you, if we have an endothermic reaction and we add heat actually to this endothermic reaction in order to proceed forward. So in this case, this heat may be added in this case. So heat can be added or rejected, and that's why in the first law of thermodynamics, we have to substitute the heat transfer with its sign. So if it is added, it has positive sign. If it is rejected, it has negative sign in this case. In some kind of reactor, so let's generalize the case. If we are talking here about internal combustion engine, we should have some work is generated out at constant volume in this case. Or we can generalize the case. In some cases, in some reaction, we use paddle wheel that actually we have shaft power in this case, input to the system just to mix air plus fuel or whatever inside actually. So we can generalize the case. This work can be either applied on the system or can be actually leaving the system. But the system, we have to say this is a closed system. So we don't have, in this case, if you have energy transfer by mass. We don't have mass in and we don't have mass out, just as the system is closed. So when I tell you we have closed the tank, rigid vessel, constant volume combustion in gasoline engine, that means actually this is a closed system and we have to apply the modified equation in this case. Type, let's apply the first law of thermodynamics. So in this case, the first law of thermodynamics, so let's start from the generalized case. First law of thermodynamics will say energy cannot be created or destroyed. So energy input to the system minus energy out should equal to the change of energy inside the system itself. Type this term should have the change of energy of the system. That should equal to the change of energy of the system. That should equal to the change of internal energy of the constituent actually of this engine. So that should equal to the change of internal energy. A change of internal energy from the reactant to the product. Plus what, Shabab? If this tank is a whole tank, if I am moving actually this tank, while this reaction, this tank is running with a given speed. And this is a rare case. So, sorry? Sorry, who?
You mean the plus kinetic energy?
Yes, exactly, plus kinetic energy.
Okay.
But for the system, Shabab, we possess the system in whole in this case. So the change of energy of the system should equal to the change of internal energy of the constituent, because there is actually gases inside, fluid, working fluid. Plus the kinetic energy. If the whole system is moving, then in this case we have to add kinetic energy. plus we have actually the potential energy. But usually the system are a stationary system, and even if they are running with constant speed, so the change in kinetic energy and the change in potential energy will also be zero in this case. So those two terms are negligible in this case. And in case of combustion, usually this term is much bigger than the other term. So in this case, we can say the change of energy of the system will equal to delta U, which is equal to U product minus the difference between the internal energy of the product minus the internal energy of the reactant in this case. Okay, so this should be actually the change of energy of the system will equal to the change of the internal energy of the constituent of this system. But what about the energy input minus energy output? This term. We said delta E of the system should equal to delta U, U product minus U reactant. But what about those terms, energy in minus energy out? We can have energy transfer in the form of heat, either in or out. We can have energy transfer in the form of work. But do we have, what is the third form of energy transfer? When we have what?
Mass.
When we have mass. So in this case, if we have mass, we should have energy transfer by mass. But this is a closed system. We don't have energy transfer by mass. So this term is zero. So we can replace this term, energy in minus energy out, by actually Q minus work. And we said we have negative sign Q minus work because the sign of the work in the first law equation is the opposite to the sign of the heat transfer. And that should equal to U product, the internal energy of product minus the internal energy of the reactant in this case. And usually, Shabab, we consider write down the combustion equation per kilomole of the fuel. So we have to add the bar here. That means actually this equation is calculated in kilojoule per kilomole of the fuel. Okay. Type we have enthalpy. We have enthalpy is equal to the internal energy plus the flow energy. H is equal to U plus BV. Okay. BV from the first law equation as ideal gas equation is equal to RT. We treat the model in this case we are following is the ideal gas model. So that BV should equal to RT in this case. Or we can say U will equal to H minus RT. This is in kilojoule per kilogram. So if I multiply it by the molecular weight of the fuel, because we write down the combustion equation per kilomole of the fuel, then in this case, if I multiply it by the molecular weight, this R will be R bar, this H will be H bar, this U will be U bar in this case. So U is equal to enthalpy, U per kilomole, this is kilojoule per kilomole, is equal to the enthalpy, kilojoule per kilomole, minus the universal gas constant, or we call it R bar or R universal multiplied by the temperature. That means this term I should have here, U product or U reactant, that should equal to the summation of number of moles of any component, any species in the product or the reactant, multiplied by H. H is equal to the enthalpy of formation plus delta H, minus R universal or R bar multiplied by the temperature. And this is how we can calculate the internal energy. So if I told you we have a closed system, in this case the first law equation will be Q minus work equal to U product minus U reactant, not H. H product minus H reactant in case of open system. In case of closed system, we don't have mass transfer, it will be Q minus work equal to U product minus U reactant. And the internal energy is the same, equal to enthalpy of formation plus delta H minus R universal multiplied by the temperature. R universal, you know this value 8.314 kilojoule per kilomole Kelvin in this case. Okay. Is that clear, Shabab? Is it clear?
Yes.
Right. Let's move forward and let's solve an example to see how we can apply the case. So for any problem, Shabab, you have to check first. Either I'm talking about an open system, we have internal combustion engine or gas turbine. This is an open system. We have flow in this case. Then we can apply the first law, Q minus work equal to H product minus H reactant. But if I'm talking about constant volume combustion or closed system combustion, then in this case I have to use the equation Q minus work equal to U product minus U reactant. Okay. طيب, let's look here. Let's look at this example. So here in this example, شباب, he said we have methane, CH4, is coming at 25 degrees C, enter a combustor of a simple open cycle gas turbine used in power plant. So usually, شباب, gas turbine consists of a compressor. This compressor is connected to the shaft to the turbine, and between the compressor and the turbine, we have actually the combustion chamber in this case. And as you know, air is coming at low pressure to the compressor. It is compressed in the compressor to high pressure, to the high pressure of the combustion chamber. So the pressure is raised here. And in the combustion chamber here, this is the air. We should add here fuel. He said this fuel in this case is methane, CH4. And the air coming here to the at the inlet of the compressor is coming at 25 degrees C, and the atmospheric pressure is equal to 0.1 megapascal. And they said actually air is coming at, so, and on the power plant is actually 400% theoretical air. What does it mean, شباب? So 400% theoretical air. So lambda will equal to what, شباب?
4.
So will equal to 4 in this case. And this fuel is coming actually to the combustion chamber at temperature equal to 25 degrees C, and same pressure 0.1 megapascal in this case. The fuel has been burned in the combustion chamber, and the exhaust gases of the combustion product has left the combustion chamber, and it has been expanded in the gas turbine. Then we can generate in this case shaft power. Part of this shaft power, شباب, internally will be actually forwarded to compressor to drive the compressor. So part of the gas turbine power on the same shaft we have a compressor. It takes part of the power of the gas turbine. And in this case, the net work out, which is the work of the turbine minus the work of the compressor, should be connected. Here we have a shaft. Usually it is connected to an electric generator. Then we can generate electrical power in this case. And here, شباب, as I told you, maybe I have told you earlier in this course, that Saudi Arabia is the top country actually in using the gas turbine. So the largest number of gas turbine in service in the world are actually here in Saudi Arabia. Usually in power plant, electrical power plant generation, and it has also, it is being in use actually in different utilities, and also Aramco using actually gas turbine in different applications. So this is a function of gas turbine and a power plant to produce electrical power, and then the exhaust gases or the product in this case will be leaving the gas turbine. He said lift the gas turbine at temperature 730 Kelvin, and also at almost pressure equal to 0.1 megapascal in this case. He said the fuel here, if this fuel is coming at mass flow rate equal to 20 kilogram per minute. And he said also the whole system. So if I want to study this system, this is an open system. So to study open system, I have to draw the control volume. We have defined the system, open system last time, as a control volume or an arbitrary region selected to do a certain study. So if we have an open system, we have flow rate in, flow rate out, we have heat transfer in or out, or work transfer. I have to draw a control volume about the system I'm going to study. And look at the masses coming in, and look at actually the masses leaving. Look at actually if we have heat transfer work in the system or we don't have. He said actually in this system, the system result actually in a heat, some heat is lost from the system. This heat lost, he said, is equal to actually 3% of the net work out. So the heat lost from this cycle, this is our cycle. Some heat is lost. Usually this heat is lost in the combustion chamber to cool down actually the gases with some external gas source. Usually we use air. So some heat is lost, but the heat lost in gas turbine is at the minimum level. So يعني, in most of the cases we assume the gas turbine as adiabatic. But here he said we have some heat transfer out of this cycle is equal to 3% of the work out. That means the heat transfer is equal to what? 0.03 of the network output of the system in this case. And we need to calculate the power output, work not net, the power in megawatt. Okay, power output يا شباب in megawatt. He give us here the work relation between the heat transfer and the work is equal to heat transfer is equal to 3% of the workload. How we should proceed يا شباب? So the first step is to write down the combustion equation. The fuel here is methane, so I will consider 1 kilomole of methane, 1 CH4 plus. We have lambda here is 4 multiplied by gamma, which is x plus y over 4, or 1 plus 4 over 4, it will be 2. This is O2 plus 3.76 N2. And that should give us, those are the reactant, should give us CO2, 1 CO2 plus 2 H2O, I think we have learned this, plus lambda minus 1, it will be 3 multiplied by 2, so this is 6 O2, plus 4 by 2, this is 8 multiplied by 3.76, this is N2, okay? And this is the combustion equation, our combustion equation that we will be using in order to apply the first law of thermodynamics and calculate the work in this case. This fuel is coming at temperature 25 degrees C. This air is coming at the same temperature, 25 degrees C. But all the combustion product, this fuel is coming at 25. Fuel is coming also at 25. And here the combustion product out of this system are leaving at temperature of 730 Kelvin in this case. I will need those temperature in order to calculate delta H, the difference in enthalpy in this case. طب that is closed system or open system يا شباب؟
Closed.
Is it closed?
Open system.
Open system يا شباب, we are talking about gas turbine in this case. We have air coming in, fuel coming in, and we have flow is leaving. Also we have exhaust product are leaving in this case. Okay, so this is still an open system in this case. Closed system, when I tell you I have a rigid tank, rigid vessel, it's a very special case for the closed system combustion. Rigid tank, rigid vessel, when I tell you we have constant volume combustion in gasoline engine, so in this case we can consider it as a closed system. Otherwise it should be open system. Okay, but here let's apply the first law of thermodynamics. It will be Q bar minus work bar is equal to enthalpy of product minus the enthalpy of the reactant in this case. But we said this heat transfer يا شباب, it has a sign either positive, negative, or it's zero. Zero in case of adiabatic, positive if it is added, negative if it is rejected. So in this case we have the heat is what?
It's rejected.
Rejected, so it should have negative sign. I should add here negative sign minus. And they said this heat transfer is equal to 0.03 of the net work, okay, minus the work that we need to calculate. That should equal to enthalpy of the product minus enthalpy of the reactant in this case. So we have a shabab here, see, this is a negative sign here. The heat as it is rejected, so it should have negative sign. So now we can say minus 1.03 of the work, that should equal to enthalpy of the product minus the enthalpy of the reactant. And here are the product and the reactant. So let's calculate the enthalpy of the product and also the enthalpy of the reactant in this case. So the reactant يا شباب, which are air plus fuel, both of them are coming at temperature 25. That means delta H will equal to what يا شباب? Delta H is the enthalpy at any temperature minus the enthalpy at temperature 25. So if the temperature is 25, that means delta H should equal to what? Should equal to 0. So at temperature equal to 25, delta H should equal to 0. So the enthalpy of the reactant in this case, so let's write it down fully. We have 1 kilomole of CH4, so 1 kilomole enthalpy of formation plus delta H CH4 plus 4 by 2, which is 8 O2 enthalpy of formation plus delta H O2 plus 8 multiplied by 3.76 enthalpy of formation plus delta H N2. We said for the reactant, they are coming at temperature 25, so delta H for all species will be 0. But for O2 and the N2, what about the enthalpy of formation? Those are natural compound at the reference point. So their enthalpy of formation is equal to what? Is equal to 0 as well. So in this case, the enthalpy of the reactant will equal to the enthalpy of formation of methane CH4. we said we can calculate the enthalpy of formation for any fuel from table A4. Go to table A4. So here is table A4. You can look here. You can look at the methane. So we have, where is methane? Yes. So this is a shabab methane, CH4. So here you will find its molecular weight, and here you will find its enthalpy of formation in this case. Okay. So this is for the methane. So I can get this value from the table, then I can calculate the enthalpy of the reactant. Okay. Like this, we can calculate the enthalpy of the product. So the enthalpy of the product in this case, product are leaving at temperature 730. So in this case, the enthalpy of the product will equal to the product. We have 1 CO2, so 1 enthalpy of formation plus delta H CO2 plus 2 enthalpy of formation plus delta H H2O plus 6. You should have for O2 and N2 their enthalpy of formation is 0. So just don't write it down. So it will be delta H O2 plus 8 multiplied by 3.76 delta H for N2. Okay. O2 and N2 their enthalpy of formation is equal to 0. But those products are leaving at temperature 730 K. Okay. But for the first species, CO2, I will be going to table A3. You will find CO2 is there. I can get enthalpy of formation. And this delta H, we can get it actually at this temperature 730. So let's look here. So here we have the table A3. We are searching for carbon dioxide first. So this is nitrogen, N2, O2, and here is it actually CO2. So this is the value of the enthalpy of formation is given here. And delta H at a given temperature, the temperature is 730. Here we have at 700 and 800, but we need at 730. We need to get the value of delta H in this case. This is delta H. So in this case, I should do interpolation, ya shabab. So I think you know about this. You are expert. So at temperature T1, if I have delta H1, at temperature T2, if I have delta H2, those are the values in the table. In this case, at 700, we have delta H. At 800, we have delta H. But I need at a temperature, which is 730, I need to calculate delta H in this case. So we can do the interpolation. We can say T minus T1 divided by T2 minus T1. That should equal to delta H minus delta H1 divided by delta H2 minus delta H1. Do you know that, Shabab? I think you are already aware of that interpolation. So we can say T minus T1 over T2 minus T1. That should equal to delta H minus delta H1 divided by delta H2 minus delta H1. So by interpolation, in most of the cases, we can approximate the relation as linear relation between temperature and delta H. So by your eye, you can just, if it is 700 and 800, 730, that means we are in the first third actually of the difference. You can look at the difference and then just increase 1/3 over the value at 700. You can do it by eye. That will be acceptable, if you don't have enough time in the exam. So in this case, this is for CO2. Like this, we can do for H2O, and like this, we have to do for O2 and N2. Then we can calculate H product. I have now calculated H product, calculated H reactant. Then I can just say minus 1.03 of the work. That should equal to H product minus H reactant. If you calculate this value, you will find the work out. So let's check this value here. So you can look at the values here, Shabab. So the work out, that should be the value of H product, and that should be the value of H reactant. We can get the difference, then we can calculate this value. It should be calculated, Shabab, in kilojoule per kilomole fuel. Okay. We need to calculate the rate of power. So first of all, this is kilojoule per kilomole. I have to convert it to kilojoule per kilogram. So in this case, I have to divide by the molecular weight of the fuel. So molecular weight of the fuel, which is calculated in kilogram per kilomole. Okay, so kilomole will go with kilomole, it will be kilojoule per kilogram. The molecular weight of the fuel, which is methane, its molecular weight is 16. So I will just divide this value from this equation by 16, it will be in kilojoule per kilogram. Then I have to take this value, the whole value here, and then I can get the work dot net out will equal to this value here, and then I have to multiply it by the mass flow rate of the fuel. This is kilojoule, this value is in kilojoule per kilogram, multiplied by the mass flow rate of the fuel in kilogram per second. So kilogram will go with kilogram, it will be kilojoule per second, which is equivalent to kilowatt in this case. The mass flow rate of the fuel is given 20 kilogram per minute, so I have to divide by 60, it will be kilogram per second. So 20 by 60. So at the end, the value I will get here, work bar, I have to divide it by the molecular weight to convert it to kilojoule per kilogram, multiply it again by mass flow rate of the fuel in kilogram per second, then we can calculate this in kilowatt. But usually the power of the gas turbine for electrical power generation is calculated in megawatt. This is kilowatt, I have to divide by 10 to the power 3, then I can calculate it in megawatt in this case. You can see, this is a gas turbine already in service. It produces actually a network out is equal to about 6 megawatt in this case. Okay, and this is the range of the gas turbine. So usually the gas turbine gives almost between 3.5 power up to 21 or 20.5 megawatt. These are the range of industrial gas turbine power output. The power output is in the range from 3.5 up to 5 megawatt in this case. Is that clear, Shabab? Mustafa, is it clear?
Yes.
طيب, let's move to another topic. I will be uploading today, inshallah, the second homework on the first law analysis. So by this, we are done with the first law analysis. I will be moving to another topic, which is the heating value today, and inshallah next time I will show you how to calculate the adiabatic flame temperature or the maximum temperature for any combustion system. Okay. Right. Let's move to the next topic. So Shabab, here, this is one important tip here. So we talk about gas turbine, and I give you the temperature at the outlet of the turbine. Here, I give you in the last example, temperature is 730 Kelvin. But what if I didn't give you this temperature? I just give you the temperature here, before the turbine. Okay, so temperature here is given. Let's say T1 and this is T2. T2 is not given, so I don't have the temperature of the product. So I will not be able to calculate delta H. So I know I cannot calculate actually the enthalpy of the product in this case. So if I give you the temperature at the inlet of the turbine and I need it at the outlet of the gas turbine, usually we assume this gas turbine as reversible adiabatic, or what's called actually isentropic. Isentropic is a reversible adiabatic process. The process is reversible. Reversible, that means we don't have any kind of losses. And it is adiabatic, we don't have heat transfer. Reversible adiabatic, we call it isentropic, because this is the only condition to have the entropy constant. We have to have no losses within the system, and we should not have any kind of heat transfer, because delta S is equal to delta Q over T. So if we have heat transfer, we should have a change of entropy. So in this case, we should not have losses. The system is adiabatic, so in this case, the process is isentropic, or entropy is constant, or the change of entropy delta S across the turbine should equal to 0. Based on the TDS relation, and I think you have seen this relation before, just equate it to 0. Consider constant specific heat analysis. Delta S is equal to integration of CV dt over T plus R ln V2 over V1. If we are considering constant specific heat analysis, I will take this specific heat outside the integration. So it will be integration of delta T over T, which is ln T. Like this, actually, for this or for the other one, we can get delta S as function of CV as well. So we have two relations. Usually we work with one relation, which is the relation as function of CV. Anyway, just equate this delta S to equal to 0. Then in this case, we can get the isentropic relation. The isentropic relation says that T2 over T1 is equal to B2 over B1 to the power K minus 1 over K. Okay? And it is the same if we have the volume is equal to V1 over V2 to the power K minus 1 in this case. Okay? If I have for the turbine, that you will need in your homework, if the temperature at the turbine inlet is given, then I can get the temperature at the outlet if I know the pressure ratio across the turbine in this case. And that should be given for you. I can give you the pressure at the outlet, pressure at the inlet, temperature at the inlet, then you can calculate the temperature at the outlet. And here you can use this temperature to calculate the enthalpy of the product in this case. But this key, Shabab, is key for what? This is the gas constant for the product, because here the combustion chamber and the exhaust gases or the product of combustion are coming to expand inside the turbine. So this is the specific heat ratio for the product, which is Cv for the product divided by Cv for the product. And the product are gas mixture. So Cv for the product is equal to summation of the mass fraction multiplied by Cv for each component. Unlike this, Cv is equal to summation of mass fraction multiplied by Cv for each component. So in this case, I have to calculate Cv for the mixture, as we have learned, Cv for the mixture, then divide them together to get the value of K. Take this K and become substitute here. We have the pressure ratio, temperature T1, then I can calculate the temperature T2, then I can go and calculate enthalpy H product. So do you have an idea about this TDS relationship? I think you in chemical engineering, you should have an idea about the TDS relation based on which we can get. This is in mechanical engineering, this is 203, the first course in mechanical engineering. Is that clear, Shabab?
Yes, but Doctor, what do you mean by V2 over V1?
B2 over B1 is the pressure at the outlet of the turbine. This is B2, and B1 is the pressure at the inlet. Okay?
I mean V2. Volume.
V is the volume of the gases. So usually this parameter, we don't care about this one in gas turbine because this is a design issue. So yeah, we don't get inside this, but it is easily actually, we have to know about the pressure across the cycle, the expansion through the turbine. So this value is well known actually for the turbine. But usually the temperature at the output of the turbine is not known. It depends on the efficiency of the expansion. Okay. So usually we can use this relation, and usually we assume the turbine has reversible adiabatic. We don't have losses. We assume we have perfect expansion in this case. Turbine has an isentropic efficiency very close to 100. It can approach 98%. Okay, is that clear, Shabab? So let's move to the heating value. I spoke with you, Shabab, earlier how to calculate the heating value of the fuel. I told you we just bring this fuel and just ignite the fuel, burn this fuel, a certain amount of this fuel with air, with a stoichiometric air actually. And then we absorb the heat from this burner, and then we can calculate this heat. It should equal to the heating value of the fuel. So the heating value of the fuel. In order to calculate the heating value, we bring actually a combustor. This combustor is fed actually with the required fuel that we need to calculate its heating value with a given amount. Then we have it is burned with air, but with theoretical air. Lambda should be equal to 1 if I need to calculate the heating value. Why, Shabab, lambda should equal to 1? Let's say we have excess air.
To get the stoichiometric, theoretical.
Yeah, because Shabab, if we have lambda is greater than 1, that means we have excess air. This excess air, part of it will be used in burning the fuel, and the other part will just act as a diluent. It will reduce the combustion temperature, and it will absorb part of the heat. So I should have error in this case in calculating the heating value. So to calculate the heating value, I will just supply the required amount of air, theoretical amount of air. Those are coming at temperature 25 degrees C, and the pressure, atmospheric pressure 0.1 megapascal. Then burning the fuel in this combustion, we can just have a cooling water circuit. Then this cooling water will absorb the heat. So this heat will be absorbed by the cooling water in this case. Okay. But then we will return the combustion product here. We should have this cooling process until we have the combustion product coming back to the initial temperature here, which is 25 degrees C, at pressure also the same 0.1 megapascal. So that means we have reactant at 25 degrees C, they burn it, we get heat, the heat has been absorbed totally by the cooling water, then the product are leaving at the same temperature 25. That means all of the heat of the fuel has been absorbed by the cooling water in this case. Okay, and this heat is called as the heating value in this case. If you apply the first law of thermodynamics, Q minus 1, this is an open system. We have flow in, we have flow out, equal to H product minus H reactant. In this case, we are studying a combustor. We are not studying the whole engine, so that we don't have work in this case. So this heat is equal to enthalpy of product minus enthalpy of reactant. Enthalpy of product and the enthalpy of reactant, we call it the heat of combustion. The enthalpy of combustion or heat of combustion. Enthalpy of combustion or heat of combustion should equal to H product, the difference in enthalpy between product and reactant. But usually the enthalpy of the product is less than the enthalpy of the reactant, because this is a fuel, it has chemical energy. So the enthalpy of reactant is usually higher than enthalpy of product in case of exothermic reaction. So that means this value always will be a negative value. And that's why this heat, we call it the heating value. The heating value in this case should equal to minus the enthalpy of combustion. Or we call it the absolute value of the enthalpy of combustion. Or it is equal to enthalpy of reactant. It will be, we can just take it other side, so it will be instead of H product minus H reactant, it will be H reactant minus H product. And we call it the heating value or the calorific value of the fuel in this case. But by the condition what, Shabab, if I ask you to calculate the heating value of any fuel. So in this case, I will not give you the excess air factor, because you should know when I calculate the heating value, the excess air factor lambda should equal to 1. It should be stoichiometric. Okay, and I will give you the temperature at which we are doing this combustion, but you have to know, in order to calculate the heating value, that the temperature of the reactant should be the same as the temperature of the product. And the heating value in this case will equal to the difference in enthalpy between product and reactant in this case. Right. In this case, Shabab, we have also the heating value. Usually the combustion product burning hydrocarbon fuel will consist of carbon dioxide plus H2O plus N2 in this case. Okay. If this H2O, as you know, if it is in the liquid form, liquid, that means actually it does not have any energy. So that means the heating value in this case, we call it the higher heating value. If this water vapor is existing in the vapor form, vapor, that means it has absorbed part of this heat to exist in the vapor form, to convert from the liquid to the vapor phase. So still it is containing part of this heat. So that in this case we call the heating value in this case as the lower heating value in this case. So if the water in the vapor form in the combustion product, we call it lower heating value. If it is liquid, we call it the higher heating value. And the difference, Shabab, between the higher heating value and lower heating value should be what? So higher heating value should equal to lower heating value plus what, Shabab? The latent heat of vaporization to convert the water from the liquid phase to the vapor phase at this temperature 25. So that should equal to latent heat of vaporization, we call it HFG. This we can get from the steam table at temperature 25 degrees C. But usually we write down the combustion per 1 kilomole of the fuel. So in this case we have to add here the mass of water vapor, MH2O is the mass of water vapor in kilogram per kilogram of the fuel input. So we have to multiply here by the mass of water existing in the product per 1 kilogram of the fuel in the reactor, multiplied by the latent heat of vaporization of water. Then in this case we can get the difference between the lower heating value and the higher heating. So higher heating value is equal to lower heating value plus the latent heat of vaporization of water at 25 degrees C multiplied by the mass of water in the product per kilogram of the fuel in the reactor. And this value, شباب, latent heat of vaporization of water at 25 degrees C, you can check on the steam table, you will find it is equal to this value in this case. Okay. But what if we have a fuel mixture, شباب? Fuel mixture. So the heating value for the fuel mixture will equal to what? Will equal to the summation of the mass fraction of the fuel multiplied by its lower heating value. So the heating value will equal to summation of the mass fraction of each fuel multiplied by actually its heating value. So the mass fraction of fuel 1 multiplied by heating value 1 plus fuel 2 multiplied by heating value 2 and so on. Okay. Is it clear, شباب? Yazid? Yazid?
Yes, Dr. Yeah.
Is it clear?
Yes.
طيب let's solve يعني a simple example. So inshallah I will end the class with this example. We need to calculate the heating value of isooctane fuel, which is C8H18 at temperature equal to 25 degrees C. So as I told you, when I tell you heating value, so you should know that it is a stoichiometric combustion, lambda is equal to 1 in this case. So determine the heating value of the fuel C8H18 at temperature 25 degrees C and 1 atmosphere using the enthalpy of formation from the table. So heating value, so I will write down the combustion equation. I know lambda is equal to 1 multiplied by gamma. For this case it will be 12.5, 8 plus 18 over 4. This is O2 plus 3.76 Me2, and that should give us 8 CO2 plus 9 H2O plus 12.5 by 3.76 Me2. And both of them are coming, reactant are coming at 25 degrees C, product are coming at 25 degrees C. That means delta H should equal to 0 for all the switches in the reactant and the product. And the heating value, he said in this case, the enthalpy, assuming the water vapor in the product is in the liquid form. So that should be liquid form, that should be the higher heating value. So the higher heating value, which is the heat transfer from this combustion, is equal to the enthalpy of the reactant minus the enthalpy of the product, or we call it minus the heat of combustion. Heat of combustion is H product minus H reactant. Anyway, so this should be H reactant minus H product. Okay. By H reactant, for the reactant, it is equal to, we said delta H as the temperature is 25, delta H for all of this component is 0. And we have the enthalpy of formation of O2 and Na2 is 0. So that means H reactant will equal to 1 multiplied by the enthalpy of formation of C8H8. We can get this value, شباب, as I told you, from table A4. You will find this isooctane. It said liquid gaseous isooctane. Because in this table you will find isooctane either in the liquid form or in the gaseous form. So you have to check here. He said we have gaseous octane. So gaseous, go to table A4, you will find the value of the enthalpy of formation. Then you can calculate this value. But what about the product? Enthalpy of the product, we said they are living at the same temperature, so delta H is 0. For N2, in this case it has enthalpy of formation is 0 as well. So that means that should equal to 8 multiplied by the enthalpy of formation of CO2 plus 9 multiplied by the enthalpy of formation of H2O. Enthalpy of formation of CO2 and H2O, we can get them from table A3, can find the value is there. Then we can calculate the enthalpy of the product. Get the difference, reactant minus product, I can get the heating value. But in this case, if you have the higher heating value, the heating value will be calculated in this case in kilojoule per kilomole fuel. Kilojoule per kilomole fuel. So the higher heating value will be H reactant minus H product. We have calculated that should be kilojoule per kilomole. I need it in kilojoule per kilogram. This is how it is tabulated in the table. So I have to divide here by the molecular weight of the fuel. So the molecular weight of the fuel. The fuel is C8H18. So 8 by 12 plus 18. So that should equal to 114. This is kilogram per kilomole. Kilogram per kilomole. Okay. So kilomole will go with kilomole. So if I divided this value, is it clear, Shabab? So yes, if I divided the value by the molecular weight of the fuel, 114, then in this case I can get the heating value in kilojoule per kilogram in this case. Usually it is measured, Shabab, in megajoule. So the heating value usually of gasoline is about 50 megajoule per kilogram. If you want it in megajoule, just divide this by 10 to the power 3 or multiply by 10 to the power minus 3. Then we can calculate this value in megajoule per kilogram. Okay. But this is, Shabab, the higher heating. Is it clear, Shabab?
Yes.
This is the higher heating value. How I can get the lower heating value? It is equal to the higher heating value minus what? Mass of water in the product multiplied by enthalpy of formation, latent heat of vaporization, HFG of water at temperature equal to 25 degrees C. If it came to your exam, I will not ask you to go to the steam table to get the value of HFG. I will give it to you. Okay. But in this case, I have the heating value. It has been calculated. Okay. And this value, latent heat of vaporization in kilojoule per kilogram, is given for you. This is the value. As I told you, this is the value at 25 degrees C. That should be the value. So this value will be given for you. So what about the mass of water in this case? This is the mass of water per kilogram of the fuel. How we can calculate it? We have the number of mole of water in the product is equal to what? Was equal to 9. This is 9 kilomole of water per kilomole of fuel. Okay? This is 9 kilomole of water per kilomole of fuel. If I need it per kilogram of fuel, so in this case I have to divide by, it will be 9 divided by the molecular weight of the fuel, which is kilogram per kilomole. And this is kilomole water divided by kilogram per fuel. This is kilogram fuel per kilomole fuel. So in this case it will be in kilomole will go with kilomole. So it will be kilomole water divided by kilogram fuel per kilogram of the fuel. Okay, is it clear, Shabab? So first of all, I will repeat it. So we have the mass of water. I'll repeat it here clearly. So the number of moles of H2O is equal to 9. This is kilomole of water per kilomole of what, Shabab? Kilomole of fuel. Sorry, Shabab? Was he speaking? So,
Okay, go on.
Mustafa, do you have input? You can have it. And we are done with the class almost, Yani.
No, okay.
So this is kilomole of water, Shabab, per kilomole of the fuel. We have write down the equation per kilomole of the fuel. So if I divide it by the molecular weight of the fuel, okay, molecular weight of the fuel, which is kilogram fuel per kilomole fuel. Kilogram per kilomole. So kilomole fuel will go with kilomole fuel. Now we have 9 kilomole of water per kilogram of the fuel. The molecular weight of the fuel, Shabab, is 114. So that should equal to 9 over 114 kilogram of water per kilogram of the kilomole of water. So that is 9 over 114. This is kilomole of water divided by kilogram of fuel. We need kilomole, we don't need the kilomole, just we need the kilogram. So if I multiply it by the molecular weight of water, which is kilogram of water per kilomole of water, so kilomole of water will go with kilomole. Molecular weight of water is 18, so that should be actually kilogram water per kilogram fluid. So that should equal to 9 by 18 by 114. This is kilogram water divided by kilogram fluid. This is water, and this is the mass of water that we need. Then we can say the lower heating value should equal to the higher heating value minus mass of water, which is this value here, multiplied by latent heat of vaporization, HFG, which should be given in this case. Is that clear, Shabab? Clear, Mustafa?
Yes. Can we just evaluate the kilogram for the water and for the fuel and divide them?
Another way, Yani?
Yes.
Yes, Yani, you are expert in that, but just Yani, leave it this way. So if you have another way to do it, Yani, for the chemical reaction, you can do it different way. But Yani, this is the simplest way. I just tried to find a way that will combine both of you. So HFG is mechanical, and the heating value is chemical. So that's a good formula. So let's have it this way.